Good morning, children. Today we'll discuss about binomial array. Let us go with the presentation. Binomial array. Now let us consider uniform linear array. How can we increase the directivity of this uniform linear array? By increasing the length, we can increase the directivity of this uniform linear array. But whenever the length may increases, the secondary or side loops may appear for the radiation pattern. So whenever these secondary or side lobes appear for the radiation pattern, some of the power output can be loss of the output power can be obtained. But for some special applications, it is desired to have only a single main lobe, but not the minor lobes. So because of these appearance of the secondary lobes or side lobes, so here the applications may be affected. So that means here the minor lobes should be eliminated completely or reduce these minor lobes. So how can we reduce these minor lobes? We will see it here. So to achieve such pattern, that means without these minor lobes pattern, how can we get? So the array should be arranged in a broadside array. That means here the broadside array, it radiates more strongly at the center than from the edges. So now let us consider the array of the two identical in phase point sources. Now let us consider 2 point sources which are identical in phase, and we have to arrange these 2 point sources with a space of lambda by 2. That means half of the lambda part. So then the far field pattern is given as E is equals to cos pi by 2 into cos theta. So the pattern has no minor lobes here. So here this is the radiation pattern with 2 point sources which are identical in phase here, and here the distance between these 2 point sources, this is A0, it is a point source, and A1 it is another point source. Here we have arranged these 2 point sources with a distance of lambda by 2, d equals to lambda by 2. So here we did not observe any minor lobes. So here this is the radiation pattern without minor lobes. So how this so here the field pattern for 2 point sources with equal amplitude in phase current. Now if you consider the 4 element array, so here we have chosen only 2 elements, but here we did not observe any side loops. But whenever you observe uniform 4 element array, that means if we arrange 4 elements, so here what will happen? We will obtain the secondary lobes. Side lobes may be appear for the resultant radiation pattern. Because why we are obtaining here the secondary lobes? Because the elements producing group pattern have a spacing greater than 1/2 wavelength. That means here for 2 elements we have considered half of the wave distance is half of the wavelength. But whenever you are consider 4 element array, the distance between them is more than the half of this lambda. So for that only here we are obtaining here side lobes or secondary lobes. So so how can we reduce these secondary lobes? So by decreasing the distance between the elements or arrays, we can distance between those point sources, we can reduce these side lobes or secondary lobes. So that means here now let us see. So this is the uh, now let us consider here, this is the arrangement of 4 elements with spacing lambda by 2. That means we are decreasing the space between those four elements here. That means this is element 1, point source 1, and here we have adjusted here point source second, third, and this is fourth. That means here we can observe here the coincidence of second element and the third element. So distance between these it is lambda by 2, and here for this here it is lambda by 2, and here we can observe this, here we can observe the double the power. So here if we consider a single element which produces here some power, but here these double point sources which acts as a single point source, but it emits the double source here, double radiation here. And here this is the arrangement of 4 element array with spacing lambda by 2. So here these are the two radiation pattern for the 2 point sources which we do not observe any side lobe. And here by arranging like this, that means pattern for 2 element array and 4 element array, this is the pattern for 4 element array. And here by decreasing the distance between the point sources with lambda by 2, so here it acts as a single element. So here that means here this point sources here 2 and 3, which acts as a single element as 2. That means 1 is to 2 is to 1. Here we can observe here this is the ratio. It emits the ratio of current 1 is to 2 is to 1 here. So here, like this, we can reduce the secondary lobes or side lobes. And here now let us consider here in the same way by in the same way like so here how we have arranged here 1 is to 2 is to 1 ratio, and here we have arranged only 2 point sources. Here the 4 element array, it is arranged as here in the center it is 2 point sources which are coinciding here. And now let us consider here this is a single element and here this is a single point source, but here we have reduced the distance between those point sources with lambda by 2, and here three elements which are acting as a single element, and here also which are 3 elements which are acting as a single element here. That means here 1 is to 3 is to 3 is to 1, like that. Here it emits the 3 times here, and here so these elements act as a single element. Here we can observe here, and here this acts as a single element which is acting here. So 1 2 3 4, 4 elements. So that means here actually here we have 1 2 3 4 5 6 7 8, total 8 elements, but here we are using here matrix multiplication method, pattern multiplication. So multiplication of patterns, by using the multiplication of patterns we are arranging. So here we can easily reduce the side lobes by arranging, by decreasing the distance here. For we cannot observe any side lobes here. And here this is a method which was proposed in 1929 by Johnstone. So the concept was first proposed by Johnstone in 1929. So here we cannot observe any side lobes in the linear broadside arrays. So now let us see. So we can arrange these. So the Pascal's triangle displaying portions of the binomial series. So when n equals to 1, that means n equals to 2 elements, for n equals to 3 elements, up to n equals to 7 elements. So here we can observe 1. For n equals to 2, we have 2 elements. For n equals to 3, we are arranging 1, 2, 3. So for n equals to 4, so here 3 plus 1, 4, 3 plus 1, 4. And here for n equals to 5, and here 1, 4, 6, 4, 1. For n equals to 6, 1, 5, 10, 10, 5, 1. N equals to 7, 1, 6, 15, 20, 15, 6, 1. So these can be observed. So here if you see 1, here also 1 1. So by adding this 1 plus 1 we are obtaining here 2. So 1 plus 2 again we will obtain here 3. 2 plus 1 3, again 3 plus 1 4, 3 plus 1 4, 3 plus 3 6 here, 4 plus 1 5, 4 plus 6 10, 6 plus 4 10, 4 plus 1 5. So here also 5 plus 1 6, 5 plus 10 15, 10 plus 10 20, 10 plus 5 15, 5 plus 1 6. So here this is the Pascal triangle displaying the portions of the binomial series. So in general, pattern for the binomial array is given as E equals to cos power n minus 1 pi by 2 cos theta. So here n is the number of sources in the array, number of elements in the array. So this is about the binomial array.